Welcome, everyone. My name is Stephen Warren, and I'm the CTO of Data Center Dynamics. And thank you so much for joining us today around the world for our special webinar with Raritan looking at designing flexibility into your data center power infrastructure. Boy, oh boy, I tell you, the news coming out in the data center industry is coming fast and furious. Topics like big data, open compute, cloud, virtualization, they get all the headlines, often overlooking the underlying infrastructure that makes it all possible. From the greatest web-scale company to the best hyperscale enterprise, you have to get down to the basics as power density is rapidly increasing in today's data center. Provisioning the right amount of power to the rack without undersizing or oversupplying the power chain has become a real design challenge and a critical requirement as we're moving forward, especially as we move towards the on-demand data center with massive power, massive requirements. So today, we're going to be breaking down today's 60-minute webinar in approximately 4 areas. The first is going to be a general overview of where the trends are taking us and what's happening. We'll have a brief poll question, but we're also going to be taking a look at the design challenges now. What are the problems? What are some of the solutions, and what are some of the benefits? What are those design challenges, and what can we do? Then we'll go back to a poll question to see where you're at, and then finally what you're really here for, that wonderful set of case studies, walking us through actual projects. So our focus today, after we hit that roundtable at the end, is how to create long-term power flexibility and improved availability for your data center operations, how to increase energy efficiency and improve SLAs through a comprehensive set of best practices, and also that ending with the case studies, real-life examples of actual data center customer problems solved and making your data centers reliable, responsive, and future-proofed. So let me introduce my colleague for today. For those of us who have been in the industry a long time, Jawahar Swaminathan does not need any introduction. We know him as a true subject matter expert on this topic. And as Raritan's Director of Energy Management Solutions, Jawahar has seen it. He has been with the clients that we all know and love. He has been with the players that are dealing with these problems, and he has understood the solutions. You know, Jawahar is based in San Francisco, and he's been working with mission-critical infrastructure and data center customers, both on the design and implementation for optimal power distribution and monitoring systems that help reduce energy usage, and the key, improve operations. You know, I'm always reminded when I speak to Jawahar that at his heart, he's that rare operations engineer who knows what we do on a daily basis, but at the same time, he's that developer friend that we've always needed and wanted. So since joining Raritan, Jawahar has contributed to the firm's entry and rapid success into the intelligent energy management segment, but at the same time, he's brought together every product that Raritan has, including the intelligent PDUs, the sensors and analytic software, also Raritan's capabilities to produce highly customized solutions for you. So I'd also like to remind everybody what Jawahar has told us many, many times. Whether you're renovating a current data center or building a new one, you have to remember to bring power to your racks that will impact project requirements and future capacity and growth now. So let's get started here a little bit, and then we're going to turn things over to Jawahar. First, a little bit of a reminder. Okay, we know worldwide data center investment growth is increasing. We know that the drivers are omnipresent. We know that investment in outsourcing space and services is continuing. And also at the same time, we know that rack densities over 10 kilowatts by the major data center hubs is increasing. But at the same time, how do we future-proof our racks with enough capacity and headroom to support server, compute changes and growth, and future technological advances? You know, how do we reduce OpEx and CapEx? How do we meet those SLAs and avoid potential outages? And also, how do we support higher, more efficient power distribution? Those are the questions you're getting all the time and having to deal with. But what did you guys respond to? So this was the question that we asked all of you when it came to jumping on and joining us in this webinar. Interesting. Do you have an upcoming data center project? About 44% of you have nothing planned yet. But if we take a look at the other numbers, we're looking at about 50% of you are dealing with projects now and over the next year. So that tells us a lot of what you're dealing with right now. So I'd like to remind everybody, you can put in your questions anytime you want. In the top, there's a question button. Please remember to do your ratings at the end of this webinar to know how we've done. But right now, let's get our first poll question of the day before we jump into the best practices. So the first poll question of the day is, what are the key design challenges? You can actually vote by hitting your voting button on the top, so that way you can look at it. Question number one, what are the key design challenges? Increase capacity, decrease cost, recover stranded capacity, right-size power distribution, or all of the above. So if you could, please start voting now. Well, folks, come on, you've got to get on here and actually vote, because I can tell you what the design challenges are. And actually what's pretty interesting is that most of you have said all of the above, everything, Jawahar. That's incredibly interesting. I mean, about 13% of you are looking at cost. 10% stranded capacity, always a key one. But all of the above, Jawahar, I got to turn things over to you right away, because quite frankly, I mean, this is a pretty important thing. So let's stop the voting and let's get going right away on things. Jawahar, thank you so much for joining us. I'm going to turn things over to you, but what are the key design challenges and how can we meet them? And what are some best practices that we can look at, or some steps in this new modern age? So over to you, Jawahar, and thank you so much for joining us.
Thank you, Stephen. Good morning, everybody. What an honor to be here presenting with DCD and meet all of you. I'm delighted to be here, and a quick shout out to the friends that I know already. Thank you for being here. It means a lot to me, and I'm hoping to get to know the rest of you that joined here as well. And it's very eye-opening to see the poll results, and as Stephen said, all of the above stood out. And why is that? We believe that all the design challenges that you see here listed are all common, and they are happening today. And these are the things that we struggle with day in and day out. We are excited to say we have dealt with most of these with our own experience, working with some very incredible minds in the industry. And as a result, we have certain experiences that we could share with you as a return to the industry that gave us the opportunity. Also, another thing that I found intriguing is the response to the registration question that we saw a chart about. It seems almost half of you have projects coming up in the next year or so, and the other half doesn't have anything planned. Why is that? We would like to take a look at it. It would be great if you can provide some more insight into why you don't have anything planned in the future. We do have, excuse me, we do have certain presumptions here. We could think of reasons like maybe management wants you to do more with less, and how do we achieve that? And that's one of the things we are looking at as a key design challenge as well, which could be recovering stranded capacity that you already have, or just right-sizing the power distribution you already have so you can utilize the capacity that exists without building new. Or could it be just that you don't have a project that's been identified? So we'll be very curious to know. We'll be very curious to know what the reasons could be, and I'm pretty sure it could be a variety of reasons. And let's take a look at some of these key design challenges that we have in mind. Increasing capacity, this seems to be the overarching reason that could even drive the rest of the key challenges that we are seeing here. How do we increase capacity without increasing the cost? That's been some of the focus for the case studies that we have coming up. And also, how do we recover stranded capacity? Let's get to the reason behind the increase in capacity that we're seeing these days. On an average, if you looked at 5 years back, if you asked a data center operator or a designer, what is your average rack density? The answer could have been somewhere in the range of 5 kilowatts. And that used to be considered the average, which you could say like medium density. And there would be leading edge players running at 12 kilowatts. That will be considered high density. But look at the chart today. Fast forward 5 years, we have 8 kilowatts and lower identified as low density, whereas 15 kilowatts and higher as high density. That's quite a shift in the density that we see in the racks. And why is that? Let's look at two of the contributing factors that stand out. One is high performance compute. It's gaining ground, and it's pretty much applied for all the major applications around. The other one is blade servers. They've been around for a while, but the adoption rate is changing. So there are various factors that we see that contribute to these high densities, but these are the two that stands out among the rest. So the trend is towards high capacity and high density, and the numbers are just jumping from 8 to 15, and we even have customers that have gone all the way up to 50 plus kilowatts, and we're excited to share some of those experiences with you. So what do we do to build this flexibility into the data center where we can address the diverse landscape of having a low density rack and a high density rack and perhaps a medium density rack within the same data center while providing redundancy and also flexibility to move things around within them? We have a set of solutions that we consider groundbreaking in terms of how it provides flexible options to deal with both high and low density configurations within the same data center or even perhaps within the same data room. And how do we achieve that? We have certain capabilities like real-time metering and monitoring that can have a high level of accuracy that you can use to reduce the number of power feeds that you bring in to every single rack. How do we narrow down the right kind of selection? So we've put together a 7-step process that's going to guide you through the way you can select the right kind of PDUs or transfer switches that go into these racks and provide the right amount of power without oversubscribing or underutilizing the capacity you have. Let's take a look at the 7-step process as we go. Step number 1 would be at a very high level. You look at the data center that you have. If this is a greenfield data center where you have complete control of how the electrical distribution is going to be, then you have all the choices in the world, all the way from 120 volt single phase to 415 volt three phase. I haven't seen any new data centers built with 120 volts single phase these days. But the majority of it have been 208 volts three phase. The newer data centers where the higher capacity needs tend to trend towards 415 volts three phase. That's been the trend we've been seeing in the past 4 to 5 years in high capacity compute environments. So determining the right kind of power infrastructure that you're going to put in place on a new data center will give you the maximum flexibility in terms of handling the ever-increasing need to move capacity up and while keeping all the different configurations within your data center for the applications you have today. This is an illustration for North America where the input voltages are in this range. If you are from Europe or Asia Pacific, the standards have been in the 230 volts single phase or 400 volts three phase, and that's been the standard for quite some time. Once we determine the overall voltage at the data center level, whether it's the new data center or the existing data center where you are constrained by what you already have, then we look at step 2 in the process of what is the demand going to be. We looked at the supply side. Now it's the time to look at what's the demand being driven by, and what are these devices? Are these switches, servers, or gateway devices, or all the other new kind of applications and appliances that come to market? What are they? How many can you fit in a rack? What kind of power supply units do they have? And what kind of power connectors they have? The industry has done a pretty good job of consolidating the various device and power connectors that we used to have into the commonly used IEC standard of C14s and C20s. Occasionally we do run into like the NEMA 520s, but it typically trends towards existing devices that have been in the data center for quite some time, and they do very specific functions that haven't been replicated by any other device. So there are applications where you do need the NEMA 520 devices, and that's another design consideration you can have while designing, whether it's going to be a delta circuit without a neutral or a Y circuit with a neutral. When you have neutral provided in the data center, you can have a single power strip that can provide both 208 volts on the C14s and C20s and give you 120 volts on the NEMA 520 circuit in the same power strip. So these are design considerations that could serve you well as you build your data center with a set of devices that are new in the market and other sets that are legacy systems that you still need to bring forward to the new data center. On step 3, we take a look at the power requirement of all these devices that we saw in step 2. We look at the nameplate value, and there are certain ways you can estimate the power requirement for a rack. One of the ways that we have found is using the nameplate value at 100%. Well, this is a very conservative way of estimating the power requirement, because the reality is the nameplate value is just a maximum power this device is ever going to draw at any given time. And that is not what your device is going to be running at. So if we are going to do 100% nameplate value, you're going to provide a lot of capacity and power to the rack that may be underutilized. So there are other customers that have taken a very aggressive approach of estimating this at 50% of the nameplate value. This could be based on their experience in the past, taking a look at all the same servers and devices over a period of time and understanding that the power draw has never gone beyond 50%. But what if there's a spike? What if there's a high demand? What if there's a peak load that comes up? How do we handle that if we estimated only 50% at the rack level? So we choose a middle ground, and we come up at a number between 70 to 80% of nameplate value to be the estimated power draw. And we can use that to determine what's the right kind of power strip or transfer switch that you need to put at the rack level. We do have a tool that's very convenient. It's an Excel-based tool. It's a 3-phase calculator where you can plug in all the numbers that you see on the nameplate values at 70% rating. Plug those numbers into the spreadsheet at different circuits and see how the power draw per rack is going to be at the total. And within this calculator, you can also move things around to make sure all the 3 phases are perfectly in balance. It's a very simple tool that we have a link to on this presentation that most of our customers have found very useful. Now we have seen the inlet side from an electrical standpoint, and the capacity needed from the load standpoint. Now, how do you bring them together? You have several options to provide the right kind of circuits and phases at the rack level. And everything is dictated by the first choice you made on the kind of voltage that you have in the data center. The plug types vary. There are NEMA standards, there are IEC standards, and there are even certain brands that provide unique and special plugs and outlets that are neither NEMA nor an IEC standard. So the choice between them is very much up to the end user and the designer to see what works the best for your data center. An IEC plug could be splash-proof and waterproof, but do you really need that in your data center? Are you okay with a NEMA-style plug that locks the outlet in place, but is not quite waterproof? Or can you accept a plug type that you see on the right-hand side of the screen, which is very simple to use, which is perfectly safe, and you will lift it. It provides the same amount of power, like a 60 amp three-phase plug. So it's very much of a design decision, and it also gives you a lot of flexibility on the power inlet side, whether you go use an overhead busway or under the race floor. Then we come to step 5, which is going to figure out what kind of remote capabilities do you really need. And this will be determined by the application that you have. Are these network racks that have networking devices that can never be turned off, or are these servers that may occasionally be rebooted for any particular reason? So we take a look at switching as one of those options, remote power control as otherwise called. Why do we need switching? We have customers making a decision on whether to add the remote switching capability into a certain rack or not, based on what is being provided by that rack. For instance, we have one customer that says we can never have switching or remote power control capability on a rack that has networking devices, because I don't want any capability for even accidentally turning things on or off from the remote, because these are highly critical networking devices that I cannot take a chance like that. And if they need any kind of service, I'm going to have on-site people deal with it as and when it's good. We have another customer that looks at the same situation and say, these are highly critical devices providing network infrastructure, and I need to have all the tools possible at my disposal if and when I need certain help, which includes rebooting that device. That's at a worst case. And then we have the other capabilities of metering. When we say metering, what level of metering is appropriate? Let's take a look at the different options that are available. We have inlet metering, which means you have 3 phases coming into the power strip, and we meter each one of them for current, voltage, and power draw. How do we make sure what we meter at the inlet level also corresponds with what's being drawn at the circuit level? You have circuit breaker metering. When you have a power strip that has lines coming in and you have them split into 3 or 6 or 12 circuits within, branch circuits, we meter each one of these branch circuits, and the net total of that should add up to the inlet metering value. Another benefit of circuit breaker monitoring would be to place thresholds on these. So if there is one circuit that's drawing a lot more power than you anticipated, let's say 80% of the breakers value. In the United States, we have breakers rated at 20 amps at 100%. So if the power draw is going higher than 16 amps on one branch circuit, then most likely something is going to go wrong, and it may make the breaker trip. What if we can set some thresholds on these so that we can take action as the operators before the breaker trips? Because even though circuit breakers are easier to service than fuses, for instance, you don't need to be looking for a fuse, and you can just flick a switch and reset them, still it has caused an outage. And the idea is to minimize the outage cost by preventing the outage to begin with. Then we have outlet metering. Why would we want outlet level metering? Well, in the same scenario that we discussed earlier, the power draw is increasing tremendously, and one of the leading reasons for that would be to just take a look at the power factor of that particular device, and you know that it's failing. When you see the power factor go down from, let's say, 0.8, which is 80% efficient, to like 0.5, which means just 50% efficient, we know that the power supply unit is going to fail. So we have customers using all these different options to bring them up and use them in conjunction with each other to provide very unique functions like load shedding, for instance, where if you know that an outlet is drawing way too much power, then go ahead and automatically shut it down based on policy that we set previously. Step 6 would be to learn the PDU or the rack power strips installation option. You have various form factors to deal with, whether it's a 0U that goes in the back of the rack and does not occupy any rack U spaces, or these 1U, 2U devices that go into network racks where you have plenty of RU spaces available. Then you would decide what kind of inlet that you have. Are these inlets coming from the race floor or from the overhead busway that you may have? And depending on that, we can provide the right kind of power strip that takes in the right kind of inlet. How about the power cord length? How does that matter? We have all seen this when we lift up the race floor. There's a big nest of cables, which could be completely avoided if you can customize the length of the power cord that you need for rack. Or even in an overhead busway application, it's the same kind of idea where we've seen plenty of instances where these power cords are coiled and they're just literally sitting on top of these racks, which could be completely avoided by just customizing the length of these power cords. In the United States, 3 feet is the minimum that you need for a power strip, so which in many cases may be adequate, or we've seen 5 feet cables being used as well. The last consideration on the installation side would be the locking mechanism. How do you make sure the power cords from your servers or switches that go into these power strips stay there? They remain with all the movements that's happening around it, all the vibrations that's happening at the rack level because of all these spinning drives and fans that you have in these devices. How do you make sure these cords don't fall out? We have several locking options where the outlets could be specially designed for locking any power cord, or you can have a specially designed power cord that could lock, or the good old method of using retention clips to keep these in place. The last step in the whole process is finding the right solution that gives you the flexibility in your data center power infrastructure would be to figure out what else is available in the market today that you might have wished for a few years back, but they are a reality today. For instance, we have customers that demand gigabit Ethernet. Today, this is a table stake feature. You have to have it. However, a couple of years back, we had one customer that wanted it, and they were the leading customer that when it comes to advances in data center technology and so on. How about Wi-Fi? How do you reduce the number of network drops that you bring into the data center by just eliminating the network drops and just have Wi-Fi? Is that something that your data center can handle? Again, Wi-Fi is yet another example where if you mentioned Wi-Fi 10 years back in a data center industry, it's going to be frowned upon by security teams. Today, it's okay. There are exceptions that you can make, and there are protections that you can put in place to enable Wi-Fi within the data center, but not enter into the security. How do we differentiate the power feeds? By using colored chassis and colored cables and colored inlet cords. Do you need automation? What is the scale of your operation? Are you dealing with 10 racks or 100 racks? When you look at the scale, it brings automation into the picture. If you have hundreds of racks to deal with, how are you going to manage these? How are you going to make sure the power strips that are in the infrastructure are updated and kept up to date? How are we going to make sure these have scheduled maintenance done without automation? Are we going to do this one by one? How do you deploy these hundreds of units in one? All these are questions that we would like to bring to the table so you are aware of the design considerations while choosing a good platform to work with. And I'm going to throw it back to Stephen.
Jawahar, thank you. Incredible, insightful information. And I have to say, moving to the next part of this conversation, which is the case studies, just proves again, I mean, Raritan's operating in 76 countries, 50,000 deployments in locations around the world, and the entire set of products. You've done it. You've been there. And by the way, thank you very, very much for also highlighting how a lot of things really have changed and also telling me how old I'm getting, Jawahar. That's not fair. Before we jump to the next poll question, I just want to remind folks of a couple of things, and my apology. Number one, this is a webinar on demand. You can download it anytime. You can pass it along to your friends. And number two, yes, we will get you the links not only for the calculator, which is fantastic, as well as links to other Raritan tool sets and documents, which brings me to, and I totally forgot this, I apologize. Jawahar, you set it up perfect. The IPDU handbook, that's available from Raritan at the end of this webinar, is fantastic. Last week I had the opportunity to read it back and forth on the way to work, and it was awesome. So let's open up that second poll question. And I'm sorry, and I love this question because it's a setup for you guys. We're trying to figure out what else is important to you. As Jawahar was saying, things have changed. So what do you think is most helpful in designing flexibility into your power infrastructure? What are you looking at now for that flexibility? Remember how Jawahar was talking about scalability, scale. So are you interested in breaker monitoring, Wi-Fi, color-coded electrical distribution, information-rich local display? I know these aren't the regular questions you get for this, but this is where it's going. This is what's happening. So vote now, and let's take a look at where we're at with the voting. So I have to tell you right now that if we take a look at what's happening in terms of things that are happening around this, most of you are really over 50% interested in breaker monitoring. And then only about 20% color-coded electrical distribution. I have to tell you, Jawahar, you're absolutely correct. And you're going to go through this one case study, which is fabulous because the white paper online is fantastic too. But this company, eBay, really took us to the next level of truly understanding the breakdown in the holistic environment and how we can truly look at how things are operating inside our facilities and how we really need to think things through. So what I wanted to do now is let's get into those fantastic case studies, Jawahar. Let's walk through them and let's really learn, because how you set things up through the 7 steps is going to help us better understand what's happening inside these critical players in hyperscale and web scale. So I'm going to turn it back over to you, Jawahar, and let's take a look at these case studies. And again, thank you so much for the insight, and let's get back to it.
Absolutely. Thanks again, Stephen. These are some of the case studies that we have prepared and wanted to present to you all. And I have to say, we find ourselves incredibly fortunate to work with some of the brightest minds in the industry, starting with eBay, Disney, and other social media companies that we've done business with. It's incredible, and I find myself very lucky to have been a part of this. and wanted to share these with you. eBay, one of the unique challenges that they have is the increasing high density in their racks, but at the same time, they don't want to change, they don't want to keep the cost going up on that. We have Disney with a similar situation where they do see the need to increase capacity, but they do not have the budget to increase the cost on bringing that high capacity into the racks. With the social media network, well, we're working with their legal department to be able to use their name pretty soon. So probably in the next webinar, we should be able to name them instead of having them as a social media network, which would make it a lot more fun. But regardless, if you look at the unique challenge that they have, they use co-location facilities for 100% of their data center footprint today, which means the cost. The cost of having another data center brought in is significant, especially when you're in a growth mode. So that's their challenge to make sure they maximize the space that they have today, and thereby maximizing the number of servers that they can put in the existing racks. Let's dive into the individual case studies, starting with eBay. So how do you reduce high capacity costs without compromising on the capacity at all? So that's the interesting challenge they have, and this is not a high capacity environment which is like a one-off. This is throughout their data centers. On an average, they go deploy in the range of 20 kilowatts or higher. And how do you deal with such high capacity which brings a lot of cost associated with it? So we work with them to figure out a way to eliminate some of the costs from these electrical distribution methods by coming up with some creative ideas to eliminate some of the things that may or may not be needed in the power chain. For instance, we can remove the power cord from the power strip, which has a certain cost associated with it. We work with Starline, who are the busway providers, to eliminate some of the components that they may not need. And then finally, we used conduits. What a creative idea in a data center. Conduits to terminate power widths into the power strips instead of using the standard power cords. Let's look at the details behind it, and this will be very interesting in terms of what the savings were. So if I can start with the savings realized, this is $1,000 savings approximately at a 17 kVA installation. So if you can save $1,000 by doing certain things differently at a 17 kVA installation, you can imagine the savings as the capacity goes higher and higher, up to like 50 kVA per rack. How do we do that? So we eliminated the power card completely from the PDU, which has an approximate cost of like $80 to $100. We eliminated the PDU's plug, which again costs like around $200, especially at 17 kVA. If you look at around like 30 to 35 kVA, those plugs are humongous, and that's a lot of copper in them that raises the price. So if we remove the plug from the equation, then you don't need the outlet on the other side either. So from the Starline perspective, from the tap box, there is no outlet, whether it's on a pigtail or on the outlet box itself. There is no outlet. So that's a significant savings of around $200. Then we eliminated the tap box cord itself. So there are no lifts, either going from the power strip or coming in from the tap box. That's another savings in the range of $20. And then miscellaneous items like strain relief and things like that. So overall, it came down to around $1,000 per rack as significant savings. So how did we do this without a cord from the PDU or from the tab box? Well, we use the conduit. So conduits are much cheaper compared to SOW cards that are attached to the power strip, and they're hard to ship and they cost a lot of money. So we just eliminated the things that could be optimized, or that could be redesigned in a way that's electrically safe and it'll pass UL. And in fact, we worked with UL engineers to figure out a way to certify these power strips in such installations, because this is the one of a kind and the first time they worked with it. So we learned a lot working with UL as to what safety means and how we design things the right way to eliminate redundant costs, but also making it completely safe for the customer. The second challenge they had was the capacity that keeps going up. So even at 17 kVA, that's not good enough. Many of you might have seen the eBay data centers. You might have taken the tour, or you might have read a lot of case studies about eBay's data center racks. And these racks can handle up to 60 RU, and they have 54U high, and they have 52U high, and they have several U spaces on the side as well. So how do you power a 60 RU rack with just 2 power strips? I mean, the traditional way would have been to just add more power strips as and when you need more capacity. But we work with them to make sure we can provide them adequate amount of power and outlets within one power strip on each side. So the end result was a 57 kilowatt power strip that takes in 415 volts 3-phase at 80 amps rating. And again, this installation did not have any plugs, because you can imagine to get an 80 amps rating, you would need a 100 amps plug, which would have been a significant cost addition to the equation. So we again kept the cost down while providing 57 kVA in one power strip. We have these displayed in trade shows, and customers find it unbelievable to see that 57 kilowatts going through one power strip. I believe that's enough to light up two or three homes in a residential neighborhood. The next use case we have is for Disney. So Disney is very interesting because for a change, my kids think I'm cool now because I'm working with Disney. They just love the fact that Daddy is associated with Disney. It's been a great experience working with Disney with regard to their new data center in Kings Mountain, where they wish to increase the capacity based on their past experience. But the data center budget they had did not allow for any excess in terms of bringing that capacity into place. So they had another challenge of how do we make sure the redundant circuits that we provide are being subscribed by the right PDUs or the right servers. They don't want people to plug in the power strips into the same circuit, like the same A feed, and then oversubscribing A while the B feed is completely open, or it's undersubscribed. So they had two unique problems, and we worked with them to make sure we can provide a solution that will keep the cost down, but also provide additional capacity. And we went to 415 volt 3-phase route to make sure they can realize all the savings that these 415 volt designs inherently bring in. We also work with them to provide rack power strips in multiple colors that matches the power scheme from all the way from the switchgear through the UPS and the PDUs. So there is no room for error. When an A feed goes into the A power strip, you will know for sure because the power strip looks green, and so does the inlet cord's plug, and so does the circuit under the floor. So everything matches, making sure there are no human errors. So here is an overview of how that architecture looks. You have a traditional 480 volts three-phase coming in at the utility level. Typically, this would have been stepped down to 208 volts three-phase in the U.S. The new design on 415 volts was to step it down just enough to bring it at 415 volts three-phase, making it a 240 volts single-phase line to neutral. So that makes it perfectly safe for the servers because they can run all the way up to 240 volts. So at a single phase. So what we ended up realizing were quite a few savings. One is from reduced transmission loss because you're transmitting now at a much higher voltage. Then the step down transformation, every time you step down voltage, you have transformation loss. And in this case, instead of stepping it down from 480 volts to 208, we're stepping it just a little bit from 480 to 415. So that reduces the transformation loss. Then we have quite an interesting savings when it comes to copper. If you have watched the commodity market these days, copper is very expensive, and the less copper you can put in a data center, the less money you're going to spend. So how does a 415 volts help? Well, when you are transmitting transmitting electricity at a higher voltage, you can get away with a lower gauge, or I should say higher gauge copper. The American wire gauge works the opposite way. So the higher number, the lower the density of copper that you use. So this is an illustration of how you can provide an average of 17 kilowatts in two different ways. If you use the traditional 208 volt three-phase to provide that 17 kVA, you're looking at a 4-gauge wire. So that's a lot of copper. So what we're showing here is the outer diameter of the inlet cord itself. It's pretty bulky. If you want to do the same thing at a 415 volts, you can get away with an 8-gauge wire. So that's quite some savings there in copper. And thereby the outer diameter of the inlet cord itself is smaller. So that's the savings on the copper side. It shows up in the amount of money you spend on laying the circuits. The circuits are cheaper. The power strips are cheaper because the inlet cords have used less copper. And by the way, this is something that's been widely used in the world, in Europe and Asia, where 400 volts three-phase providing 230 volts line to neutral has been the standard for a long time. So this is a proven technology that doesn't increase any risk on the customer side. So they were very happy to go with this and realize all the cost savings that the 415 volts inherently bring you. Here's another illustration of the same idea, where if you want to raise the amount of capacity that you provide to the racks, you have a couple of ways to do it. You can either increase the amperage, or you can increase the voltage to get to the same result. So this is an illustration where if you kept the amperage the same, but increased the voltage, then you can see how much of an impact that it has. So at 208 single phase 30 amps, you're only getting 5 kilowatts, enough to power maybe like 20 to 24 servers. Whereas on a 30 amps 3-phase 208, you can almost double it to 8.6 kVA and support up to like 40 devices. The third one is 415 volts 3-phase. At the same 30 amps, you're getting a doubling effect of 17 kVA, thereby supporting a lot more servers. So if you have blade chassis, for that matter, you can support 3 to 4 of them in each rack quite comfortably. The last case study that we have for you is from the social media company that we've been very fortunate to work with. They have a very, very aggressive growth target, both from a financial side and also from a capacity side. So they do not want to increase their footprint when it comes to the data center space while increasing the capacity and the density of the racks. They started with an average rack holding 30 to 35 servers at the max, while they have an L2130 circuit. So that gives you 8.6 kilowatts per rack with a three-phase 30-amp circuit. But that's not quite enough, because what they have also realized is they don't need all those 8.6 kVA all the time. They're running at about 50% of the load. So why do we have all this capacity left, but not add more servers to it? So the solution that we came up with was to right-size the rack with 40 to 42 servers per rack, while keeping a very close eye on the capacity. So that if any time the load goes higher than a certain amount, then we would have automation built in that can go ahead and trigger certain actions to release the load from that particular rack. So this is the social media company, the case study that we have, where you'll see there's a reason why we have built modeling accuracy by much emphasis to the monitoring in this particular case. When we load 40 servers in a single rack, but keep the capacity still at 8.6 kVA, there is very little headroom left for any kind of unexpected peak loads. So in those scenarios, what we had to do was to manage every single circuit very carefully. So the circuit breakers, in this particular case, there are 3 breakers that are protecting each of these branch circuits. Each of those breakers are monitored closely, and the accuracy on those is plus or minus 1%. So how does that matter? So let's say if the accuracy is plus or minus 5%, that means you can leave 5% of the capacity that's available to you on the table, because you don't know for sure if you have that or not. Now, if you multiply that by the hundreds of racks they have, that's quite a lot of capacity that's left unused, which you already have, you're already paying the co-location provider for, but not utilizing it. So that's how we decided that we came up with the solution to closely monitor these circuits and take actions based on it anytime the load goes over a certain threshold. And we can keep the customer happy by providing them the most number of servers that he can provide, that he can put in one rack, while keeping our capacity exactly the same as before at 8.6 kilowatts. So that concludes the case. I'm going to send it back to Steve.
Jawahar, I have to say, thank you very much. Incredible insight. I wanted to try and change things up with this roundtable. We've got some questions that have come in from the community during the webinar. We also have the questions that came in from all the research that's been done by Raritan and DCDI. But what I'd like to first ask you about right up front, capacity. You spoke about it. You know, we've been hearing a lot right now, especially in the content community, the web scale community, are talking about issues around overcapacity in the bottom of the rack and then underutilization at the top of the rack. And you spoke about this in all 3 examples. Is that something that you're seeing more and more as you're meeting with clients? And is it beyond web scale? Is it also those in the hyperscale market, those that are looking at hyperscale as an opportunity?
Absolutely. Great question, Stephen. Stranded capacity is what it basically is, right? So you have capacity at the rack, but you don't know exactly where it is. Sometimes these are, sometimes the servers and devices are loaded just in a fashion where it doesn't utilize the entire power strip and the entire power that's provided by all three phases. So we have seen instances where the rack is half full because the servers are pretty dense and they take up a lot of power. So, for instance, you have an 8.6 kilowatt rack, but you only have 20 servers in them, but those 20 servers are already drawing a lot of power. That's making it run very close to 8 kilowatts. Now, that means the top of the rack is completely empty, and more often than not, we see that the power strips, all the top of the top half of the outlets are all empty as well. So what it actually does to the entire data center power chain is that it loads one or two circuits more than the other, creating harmonics issues that are very bad for the data center. So we have created some solutions for working with customers where we can have these phases balanced in a way in the physical design itself. So the power strip will look like it's split into two halves, and the bottom half is one three-phase power strip with line 1, line 2, and line 3 circuits, and the top half, another three-phase power strip with line 1, line 2, and line 3. So remember, this was still one power strip with one inlet cord of three-phase coming in, but we're just splitting the circuits in two different halves so that even if you have a half-full rack, you are going to have a perfectly balanced rack instead of having to deal with issues upstream on your power chain. So that's one thing that we've done, where we can make sure we recover the stranded capacity because of the space imbalance, if you will. The other thing we've done is to meter it very closely, like in the case of the social media companies use case, where we have the metering accuracy that provides 100x multiplier for every 2% or 3% that we leave on the table.
Well, thank you. That's a perfect example. And we've actually spoken about understanding capacity, and you've covered understanding cost, and you've also talked about understanding capability. And you are too right in telling everyone that we really need to keep a close eye on what we're doing and understanding what we have and where we're going with our density issues. So look, we're nearing the end. Jawahar, I want to say thank you so much. We've only got a few minutes left. I'd like to remind everybody, please rate the webinar. I know that this was full of a tremendous amount of information. It included a lot of the crown jewels from Raritan. And by the way, there's a lot of great examples out there from Raritan of fantastic case studies, financial services firms they've worked with, internet sites, banks, enterprises, pharmaceuticals. It's more than just what was mentioned here. So reach out to Raritan and get that information. I'd also like to say, please, we will get back to you with information on the cost calculators. We'll get back to you with information. Please reach out to us, both at DCD and Raritan. We will be, make sure, please download the webinar, pass it along to folks. If you want a PDF copy of it, please reach out to us at Raritan and DCD. We'll help you out. Also, don't forget to download the iPDU handbook. I'm telling you, for a guy who rides the train an hour and back and forth to work, it was one of the best things for me to have last week on an iPad. So thank you also. And folks, thank you all for joining us. This is the end of our webcast today. Again, my deep appreciation to Jawahar for taking of his time, but also to Raritan for really reaching out to its customers and letting us find out and learn from them. So once again, appreciate all your time, Jawahar. A big thank you also. So folks, at this, I'd like to say thank you for all attending, and please learn more about Raritan's Power Solutions by reaching out to them. They are the player you want to be engaged with as a partner, as Jawahar has told you. So to everyone, thank you for joining us. Don't forget to rate us, and please do remember to reach out to Raritan. Thank you all.